Hello everyone and welcome to my YouTube channel. In this video we'll be discussing the INMO 2024, which is the Indian National Mathematical Olympiad. So far actually we've discussed for this specific year. We discussed first of all the IOQM, and after the IOQM we discussed the RMO as well, and now finally we're discussing the INMO, which is like I think the last test, like basically to get to the to qualify, basically to train in the camps and stuff like that. And of course after that eventually students will go for the TST, the team selection test, in order to qualify to represent India in the IMO. Okay, so let's see some info about this Olympiad. First of all, we've got 4.5 hours, and we have actually 6 problems, as you can see here, 6 problems. Like the maximum marks is 102, so each question is worth I think 17 points. Of course, like all questions, the answer alone is not enough. You need to prove, right? Okay, so that's what we'll be discussing in this video. I hope you guys excited. What are you waiting for? Let's get started. Alright, so the first problem is a geometry problem. We're given a triangle ABC, an isosceles triangle, so CA equals CB, and then we're given a point E that lies on the circumcircle of ABC, such that ECB is 90. Then we're going to draw from this point E a parallel to the side BC, so that it intersects CA and AB in F and G respectively. We need then to take the center of the circumcircle of EGB and show it lies on the circumcircle of ECF. Okay, so let's go for a diagram, and as we always say, first of all, don't immediately draw a big diagram. Draw a small diagram, sketch a very quick diagram, in order to see what's the question all about. And in order for you, when to draw the big accurate diagram, not to get some points outside the page. So let's start doing that. Clearly we're going to need the circumcircle first, and we're going to need to have an isosceles triangle. So let's choose these and then take a point here. So now we have our triangle CAB. Then we're going to take a point E such that ECB is 90. So we're just going to take here a 90 thing. You can actually just, if you have the O, when you draw the diagram, you can just like connect this thing here and get your point. So this thing here is 90. Anyway, so this thing here is E. Now what we'll be doing is taking a parallel to CB from E, and now we have 2 points. CB, parallel to CB, so that intersects CA at F. Yes, so CA at F, here we have F, and here we have G. Next we'll be taking the circumcenter of the EGB triangle. So this triangle, the blue one, EGB, I'm going to take the circumcenter somewhere, maybe here. Let's call it O prime. And then what we need to show, that this O prime actually lies on the circle ECF. So something like this. Okay, first of all, it seems that our diagram is very simple, and thus we can indeed draw a very, very accurate diagram immediately, and it's really like kind of simple. Of course, our plan, as we did here, we can first of all draw the circumcircle of ABC, then just take some like points A and B, and just take the perpendicular bisector to get C. Yeah, that's simple. Or actually you can just start by doing C and then taking your protractor to make your compass in order to make these two equal. and now you have an isosceles triangle. Then you can just take, because you already have your O, take the point E easily, and then you just draw a parallel, which is very simple. Construct the parallel to BC, and hence everything is very accurate. The only challenge is to get O prime. And how to get O prime? Actually, it's simple. You just need to do some perpendicular bisectors, right? So just locate the midpoint here and draw perpendicular. And also you can locate another midpoint, maybe for this actually, because it's the diameter. You already actually know it's O itself. So you can just take a perpendicular from O to this, and you're going to get O prime. So let's immediately do that. Draw a big diagram. Let's take points here, and let's say C is here. It's very important to draw accurate diagrams because they're going to help you, especially when you get some nice properties on your diagram. If we say O is somewhere here, let's say E is somewhere here, such that this thing here is 90. And now we're going to take the parallel line. These are the points F and G. And as we mentioned, we're going to take the circumcenter for this triangle. Just going to make it a blue so that we keep it in our minds. Okay, so we're going to do it actually something like this. And as we said, like you can actually join AB, like it's going to be at O, and you're going to do it. Now actually, I want you to really draw an accurate diagram at C, whether you're noticing something nice. If you didn't notice anything, then actually your diagram is bad. Because, believe it or not, the point O prime is going to actually, if you're drawing a very good diagram, it's going to lie on BC. So something like this, if you just, like somewhere, maybe here. If you just intersect two perpendicular bisectors, you will see that this point lies on the side BC. And remember our rule of thumb, when we're drawing a very accurate diagram, and we're not taking special cases, like everything is good. For example, we didn't do this thing to be equilateral, we made sure not to do that. If we get something nice, then probably it's not a coincidence, right? So probably that this thing is actually correct, always. Okay. Of course, let's see whether this will help us, if it was there or not, because of course right now we need to prove it lies there, as we didn't really prove it. Of course, remember that our task is to show that this thing is cyclic. This quadrilateral is cyclic. This is our main task, to show that this thing is cyclic. Let's see. If it's cyclic, of course, what does that mean? That means that, for example, if this was on the sides, this thing is going to be, of course, C. And hence this thing is going to be C as well, right? This thing is going to be C as well. Is it really C? Let's see. So O prime EG. Right now, of course, what are we doing? We're seeing, is it really true that O prime must be on the side BC? We're just checking. So if this thing is C, actually, let's see. If this thing is C, then yes, it is. How can we calculate this angle? How can we trace it? Well, remember, O prime is the circumcenter for the triangle EGB. EGB. And remember, we can actually, whenever you have a circumcenter, then you can find all the angles. If you don't know how, then check the EGMO video, the angle tracing video that we did in our geometry playlist. This thing is very simple. You can actually just immediately do something like that. You can draw this thing here. And remember that this angle here is twice as this angle. Twice as this angle. But what's this angle? Guess what? Because we know that this thing here is 90. So that means that we do know actually what's this arc. if this arc was C, then this thing 90 minus C, right? 90 minus, so this thing here is 90 minus C, and hence this thing here is just this angle here is 180 minus 2C. Because this thing is isosceles, that means this thing indeed is C, and the other one actually is C as well. So yeah, guess what? Our prediction was correct. This point, if we can show that it lies on the side, then we're done actually. So now this is our new goal, as you can see. Our goal is to show that the circumcenter doesn't really lie here on just the circumcircle of this triangle here, but to show it lies on CB. If we can show it lies on CB, then we're done. Okay, very good. So how exactly can we do that? Basically, of course, you can do many things to do it or to prove it. So one idea is to use phantom points, because there are many ways to do such a problem. For example, will you choose the circumcenter and then show it lies on the side? Or maybe you can do something else. Maybe you can take a perpendicular bisector here and let it hit this side at a point and show that this point indeed is the circumcenter. Another option is to choose this perpendicular bisector. Another option is to choose this perpendicular bisector. So you have actually many options to do. Probably many of them solve the problem. But here, what we'll be choosing is this one here, the perpendicular bisector of this particular line, because actually this line is really nice, as this thing is only related to the it's actually the diameter of the circumcircle, right? So right now, if we define O prime to be the intersection of the perpendicular bisector of EB with the side, we're going to know that these guys are equal. Our goal is to show that O prime is the circumcenter of EGB. Okay, very good. How can we do that? Let's do first of all some angle chasing. So let's do some angle chasing. Okay, what angles do we know here? Exactly, let's see. So if I join this EB, we know that this thing is isosceles, right? And of course, remember that we know these angles because we know the arcs, since this thing is just 90. So for example, what's this angle here? The arc EC. Clearly the arc EC is just 90 minus A or B. Remember, A and B are equal because it's isosceles triangle. So this thing in total is 90. This thing is A. Then that means this thing here is just 90 minus A or 90 minus B, the same. So 90 minus B. Of course, that means this thing here is 90 minus B, and hence this thing here is 2B. Very good. So that means we've got one angle for the circumcenter. E O prime B is actually 2B, 2 times B. Is this enough actually to solve the question? Well, remember, we already know it lies on one perpendicular bisector. So if we can get one angle that's related to the circumcenter, then yeah, that will be enough. Because there are not so many angles on the perpendicular bisector that gives you 2B as well, right? You can only have one 2B. As you can see, if you keep moving like above, you're going to get the angle is going smaller, right? So if we can show that yes, this must be 2B, then we're done. Of course, this angle should be have a relation with this angle, right? If you remember, in our UGMO video, we said that when you have an obtuse triangle, then something like this. If this was x, then the angle for O is going to be 360 minus 2x. The reason is simple. This angle should be 2x. So that means this thing is 360 minus 2x. So let's try to find this angle, can we? Sure we can. Let's see. Remember the parallelity. We know that this thing is parallel to this. So automatically we know that this angle is P. And hence this thing 180 minus P. You can of course check that 360 minus 2 times this is going to give you 2B. And hence O prime indeed is the circumcenter of EGB. And hence we are done, because we have shown that this point, which is the circumcenter, lies on the side BC. And hence this angle here is C. And we already showed previously that this thing is C. And hence indeed it's cyclic. And so we're done. So as you can see, the main thing was draw a very accurate diagram, Because imagine if we didn't draw an accurate diagram, we will never notice that O prime will lie on BC, and hence this will make our life way more complicated. After we did that, we just checked that this is actually equivalent to solving the question because of these two, like C here and C here. And of course, then the rest was really some simple angle chasing. We actually choose kind of a nice way, which is to do a phantom point here, the perpendicular bisector of EB with the side. That immediately gave us the angle that we're looking for. Yeah, basically that is the problem 1. As you can see, this question is really not that much difficult if you have good experience with geometry. Let's go to problem 2 now. Alright, for problem 2, we're given a combinatorics X question. As you can see, we have a grid or a board of 24 times 2024. That is colored white. All the squares are colored white. And now, in each process, what we can do is we can choose either one column or one row that has all the squares of it. All of them, they are white. What can we do? We can simply choose 1000 squares and change their color to red. And of course, our goal is to maximize the number of squares with red, that are colored red. Okay, so let's try simply to do or find some example. Let's try to find the maximum number. Okay, so here I'm going to assume we have 20 times 24. And so on. And same thing here, columns, 20, 24 columns. Okay, let's start trying this process. So first of all, let's, for example, pick this column. This row, I mean. If we pick this row, all of them are white right now. So we can choose 1000. So let's say we choose like these ones here. Let's color them red. So the first like 1000 here. We can also do the same thing for the second row, right? Choose 1000. Of course, our goal is not like to make them random. Let's try to make them like under the same thing. Okay, if we do this for all of them, then now we've colored actually how many? 2024 times 1000, right? So far 2024 times 1000. Very good. Now of course we cannot choose any row anymore. So now we need like to put here a limit. And now what we have is we can choose actually columns, right? We cannot choose these columns. They're already like red. So we can choose these guys here. Of course, how many do we have? Here we have done, of course, 1000. So now we have remaining 1024. So we can simply do the same process here. We can choose 1000 here, 1000 here, 1000 here, so on, 1000 here. So that will give us just an additional 1024 times 1000. So this is basically like the answer in our case. Of course, we cannot do anything anymore because these guys here, we cannot choose the rows nor the columns. So yeah, basically what we found here, we found an example where we have 3000. Yeah, basically this is the answer, 3,048,000. Okay, this is like our example. Is it really the best one? Well, the question seems kind of simple. Probably this thing indeed is the simplest one. Actually, I mean the maximum one. Because we're kind of doing it very logically. So let's see, can we really do a formal proof for this? Let's like take the board again and think about it. Alright, 2024 here and again 2024 here. Okay, so when we start, clearly we're going to pick either a row or column. Assume without loss of generality we picked one row. So if we pick some row here, then we're going to choose some squares that are red. Again, assume without loss of generality that we are going to pick the first 1000, right? It doesn't actually matter because we can play with the swap like with the columns right now. So let's assume we pick this and this like the first, basically 1000. So let's say something like till here. Okay, now let's see what can we do in the next step. Now, what we can do actually, if you look at the columns, now all of these columns are screwed. We cannot choose them because they all have a red thing in them, right? Remember, the condition of the question is we cannot have any red. All of them should be white. So now the first 1,000 columns are done. They are like we cannot choose them at all. So that means that the maximum number of columns possible is we can choose these guys here. How many columns do we have here? Of course, we have 2024 minus 1,000. So at most, now the number of columns is simply 1,024. What about the rows? Clearly, the rows actually we can choose all of them, right? In addition to the one that we have. So that means the number of rows now is just 2,024. And indeed, this is indeed like the maximum thing that's like possible. And of course, you can clearly see that this actually is exactly our like answer here. We add them and multiply by 1,000 because we are doing 1,000 in each coloring process. So yeah, basically that's it. We're done. As you can see, this was a very easy computerized question in which like you literally just do the simplest example possible, and then the proof actually is very easy as well. So now let's move on to problem 3. For problem 3, we're given a number theory question. You can see that we have a prime, an odd prime p, and we're given 3 integers a, b, and c, such that this thing, this, and this, they're all divisible by p. We're asked to show that p divides each of a, b, and c. Okay, very nice. We need to show p divides all of the numbers. So of course, if you can look at this, you can easily see if p divides one number, let's say it divides a, then because it divides all of this, it must divide this thing, right? And of course, if it divides this, since p is prime, then it divides p. So if p divides any one of them, like let's say a, then you will get p divides b. And if you look at anything else, let's say this, you will see that it divides c. So if p divides any, then it will divide all of them. So now let's assume that p doesn't divide any. It doesn't divide a, nor b, nor c. So now we're assuming p doesn't divide a, nor b, nor c. Okay. Now, what can we do? As you can see, we have something like this thing is congruent to 0 mod p. This thing congruent to 0 mod p. This thing is congruent to 0 mod p. So if you look at this, because these guys are the same, one very nice idea is to do something like this. Mod p, of course. Remember, these guys all are not divisible by p. So you can actually divide, right? You can just write this thing as a divided by b to the 2023 is congruent to -1 mod p. Very nice. So now this thing to the 2023 is congruent to -1 mod p. This strategy is really cool because instead of working with two things, now we're just working with the division, right? That's actually much simpler to deal with. So let's assume something like this: x is equal to a over b, y is b over c, and z is equal to c over a. Clearly now you can see that from the number 1 we can get x to the 2023 is congruent to -1, right? In fact, you can do the same for the other guys, and you can just see that all of these, like now we'll get y to the 2024, and here z to the 2025. They're all congruent to -1 mod p. So now this is basically our question. And of course, don't forget that x, y, and z, they have a relation. As you can see here, their product is 1. So we always should notice the condition where x, y, z is 1. Okay, now instead of working with this question, we can work with this question, and our goal is to get a contradiction somehow. Okay, so let's look at this and think, how can we do this question? Okay, first of all, of course, we want to get this involved. The easiest thing to do is just to maybe take this to some power. Probably the best power is just 2024. If you take everything to the 2024, you can get these involved immediately. So if you look at this, yz to the 2024, of course, this thing is already 1 from here. Y to the 2024 is -1. X to the 2024, it's actually, from here you can easily see that it's just negative x, right? So now x became negative x. Y became -1. What about z? Z actually here, it's 1 over, or actually -1 over z, because it needs another z to become 2025. So yeah, 1 is congruent to this thing. And of course, immediately you can see that that implies that x is congruent to negative z, mod p. Very nice. Now this thing is a very nice relation. We got a relation between x and z. In fact, we found z using x. You can say something like this. Okay, now actually you can get this here. So if you just plug it, you're going to get that x squared times y is congruent to negative 1 mod p. This thing is also nice. But actually, more importantly, because we found a relation between x and z, we can just plug it there, right? So let's plug instead of z negative x. So now we have that x to the 2023 is congruent to negative x to the 2025. Clearly, this immediately gives us we can cancel the x to the 2023 in both sides. We can just see that x squared here is congruent to negative 1 mod p. Okay, this is very good. As you can see, we are actually simplifying more and more. So we found exactly the value for x squared. Looking here, we can actually plug x squared, right? We can plug negative 1, and hence we found y itself. So that means that y is congruent to 1 mod p. Very nice. We found y itself. Y is 1 mod p. Remember, we know y to the 2024 is congruent to negative 1, and hence 1 is congruent to negative 1, and hence p must divide 2. And of course, that's a contradiction because we know p is an odd prime, so it cannot be 2. And basically, yeah, that's it. We're done. Again, a quick recap for this question. This was really very standard question. The basic idea was to try to hit this with mod, and instead of working with 2 stuff, just divide and make it 1. This is very like a common thing. If you have just some experience with mod, this idea you must have gone through this idea, especially when you're doing Fermat's theorem, like when you have something like this, x to the like n minus y to the n. You can just like make this 0, p divides this, and move this to the other side, and then bring it and divide to make it x over y all to the n is congruent to 1. So yeah, this idea is very standard. Just create these x, y, z, and their product is 1. Don't forget the condition. And now just play with them somehow, like play a little by a little, and you will immediately see that y is just 1, which will kill the question. Alright, so we're done with problem 3. Now let's move on to problem 4. Alright, for problem 4, we're given like a definition here. A cardinal set S is a set of positive integers that contains the integer cardinality of S. What exactly is this cardinality of S? It just means the number of elements of S, or the size of S. So let's say S contains the numbers from 1 till 10. Then simply the cardinality of S is 10. So they're just saying here that if we have a set, some set here, and this set, like let's say it has like a1, a2 till an, then if the number n is here, then we say S is cardinal. Of course, as you know, when we're dealing with the sets, we don't allow repeating elements. So if you say like 1, 1, 1, for example, when you do a set, automatically you delete these and you just keep a single one. So keep that in mind. Okay, so now we understand what is a cardinal S. They are telling us that we have some function f from z positive to z positive, such that for any cardinal set S, f of S is also cardinal. What do they mean by f of S? Well, simply when you evaluate a function on a set, let's say this is our set till an, then when you like what's f of S, it's simply f of a1, f of a2, and so on. Of course, as we said, if we have something repeating, we delete it. So they're telling us if S is cardinal, this thing is cardinal, then this must be cardinal. Again, be careful. Here, this does not have any repeating stuff, so n belongs here. But here, that doesn't mean that n must belong here, because maybe some numbers here, some values are equal, and hence now it might change. Let's say these guys are equal and the others are all distinct, then that means we should have n minus 1 belongs to this. So yeah, be careful. Okay, so they simply are asking us, after they gave us this function, to find all possible values for f 2024. So probably we'll be analyzing generally the values of f of n, what are the possibilities for it, and of course eventually we'll just get 2024 as just some number, right? We're just going to plug it there. Nothing special when you see some fancy numbers. Okay, so let's go ahead and start working with this problem. First of all, the only thing we can do here is try to pick some examples, right, at the beginning. So let's try picking some examples for S, the set S. We can play with the set S. So let's pick, for example, S containing one element. If we want to like the set S to have only one element and its cardinal, one must belong to the set, and hence we can only pick the set of one. If we pick that, of course, what is f of S here? It's just going to be f of 1. This thing is cardinal, so it must be the set 1, and hence we just concluded that f of 1 must be 1. Okay, that's a nice thing to know. Very good. Okay, let's continue. Now let's pick two elements. If you want to pick two elements and we want our set to be cardinal, then we're going to pick number 2 and something else. Number 2 and something else. For example, if you just pick 1 and 2, then that just will give you that f of S is going to be, okay, f of 1 we already know it's 1, and we're going to have f of 2. Now this thing is cardinal, so actually here you have two choices, two possibilities. Either f of 2 is 2 and hence it works because 1 2 is cardinal, or actually f of 2 can be 1 itself. If it is 1, then we just have like the set 1, which is cardinal, as we said. So now, as you can see, we have two possibilities. F of 2 can be either 1 or 2. Alright, very good. Okay. Actually, you can take 2 and any other element, 2 and any other number. If you take 2 and any other number, f of S is going to be f of 2, which is either 1 or 2, and the f of the other number. And you'll have actually a bunch of possibilities here. In fact, if you try to look at this generally, of course, you can play with other stuff like S, like maybe 3 numbers and so on. But if you just look right now, generally speaking, let's take a look at some S. General. Okay, let's say the number of elements here is k, and the other numbers are like a1, a2, and so on till ak minus 1. Now here we have k numbers and k is there, so that's good. Okay, so this is the cardinal, so that means f of S should be cardinal, and that is just f of k and f of the other guys here. Very good. Okay, so this thing must be cardinal, this set. Of course, as we said earlier, we don't know how many elements here, because we cannot just say k, because as we said, maybe these numbers, some of them are equal, right? So we don't really know that. However, actually, since these numbers are random, I mean, like, we can choose the AIs. If we actually can pick f of AIs so that they are not equal, all of them are distinct and they are not equal to f of k. Okay, when can we guarantee doing that? We can guarantee that this is possible when f is unbounded, right? If f is unbounded, that means like we can always have large values for f, it's unbounded, then that means that yes, we can do that. So here actually we can discuss two cases. Case 1, f is unbounded. Okay, in this case we can just simply choose a1 less than a2, so on, such that f of a1 isn't equal to f of a2. They're all distinct, basically. Let's say they're distinct. Are distinct. In fact, we can just even say like f of k. Okay, so if all of these are distinct, then Very good. Then that means we now know how many elements in this set, since they are all distinct. It is actually k. So k must belong here. K must belong here. Okay, but now you might tell me that like our goal is to say this thing must be k, but you might say, okay, one of these should be k, can be k. So no problem, we can just add this. Remember, it's unbounded, so let's pick the AIs to satisfy what we want, right? Let's even delete the k. So we can just do that now. Of course, sorry, right now I cannot say this because maybe k equals f of k. So maybe we can say something like, okay, this, and we can just say that k and these guys are distinct. So k isn't equal to any of these, right? None of them is k. So yeah, you can just like play with this. Maybe like you can use the max function here, whatever. So yeah, that works. Okay, so yeah, not really the max function, but I think you get my point. We just want to guarantee that these guys, none of them is equal to k. Okay, now since we did that, that just immediately gives us that f of s is equal to k. And so one of them should be k, and none of this is k. So that means automatically that we have just shown that f of k equals k for all k's. Okay, so in this case we actually have f of the function f of x is equal to x, and hence f of 2024 is just 2024. And of course this works. You can check that f of x equals x works. You can just like look right now, because it's literally the same, right? F of s after all is just s, the identity function. So yeah, that works. Okay, so we're done with this case. The other case, if it's bounded, f is bounded. Okay, now if f is bounded, we cannot do this anymore, because these guys, even like if we change AIs, they might still give us the same values. So now we'll be playing on this bounding. Because f is bounded and we have infinite amount of numbers, positive integers, then there exists an infinite chain, of course. So there exists an infinite chain. We can just make them order, actually strictly, and so on, like ak, and so on. It's an infinite, such that f of a1 equals f of a2 equals like till f of ak, and so on. They all equals something, so some value, right? Let's call it maybe alpha. Okay, so if all of them are equal to this alpha, then we can simply pick a set S, define a set S to be like containing these numbers. Of course, what we going to do, we're going to put these numbers. Let's pick A1 numbers, right? If we pick A1 numbers, so we're going to keep doing this till we get A1. So this thing is cardinal because how many elements here? A1, and we have A1 there. Now f of s, clearly f of s, it's f of these guys, but all of them are equal, hence it just contains a single number. It actually only contains alpha. So this must be cardinal. This is cardinal. So this thing must be cardinal. Of course, that just means because the only cardinal set with only one element is 1, right? Hence that means alpha equals 1. Very good. So we've just shown that if we have an infinite chain, then it must be 1. Like all the elements, their images should be 1. So that means we only have a single infinite chain that has like all the values have if they are f as 1. Very good. So let's say that we have right now, of course, we have two possibilities. Maybe all the numbers have if their f is 1. So we can say either f of x equals 1 for any positive integer, and of course this works. Actually this works because whatever, like you have a cardinal set, always f of s is going to be 1, right? The set 1, so, which works. So that means here in this case we get f of 2024 is just 1. So yeah, this thing works actually here. So far let's collect our answers here and here. Okay, but we have another possibility, which is no, actually we do have some other value, right? We do have maybe like let's say something like, let's say y, such that f of y isn't equal to 1. Then what does that give us? We can simply now choose S to be our same chain, original chain, the same chain again. We can now put y here, and we can put the numbers again. Okay, maybe now I'm going to make them again a k minus 1. Sorry, not k, I mean a1 minus 1. So now, how many elements do I have here? I have here basically a1 minus 1 element, and plus this, it's 1, so it's a1. Okay, actually you might say that a1 is 1, so maybe you don't want to do that, so you can instead choose something for a2, right? You can maybe say a2 minus 1. So that also works, because how many elements do we have here? a2 minus 1. And how many elements here? Like 1, so it's a2 in general. So this thing is cardinal. This thing is cardinal. So that means that f of s, what's f of s? All of these are equal. So that just means that all of these actually are 1, right? So 1 and f of y. So that means this thing is cardinal. This thing is just cardinal. Of course, now, as you know, we know f of y is not 1, so it must be 2. So f of y is 2. Very good. That just means that if we have something not equal to 1, there its f is not 1, then it must be 2. Okay, this seems reasonable. This seems good. So that means that f of 2024, if you look at it, it might be 2, right? Yes. In this possibility, the only like it's either 1, which we already like covered, or it can be 2. Remember, the question is not asking us find all f. The question is just telling us what are the possible values. Let's see here for f 2024. Here in the first, so far in the first case, when it's unbounded, we show that it must be 2024. But in the case it's bounded, we saw we have two cases. In the first case, it must be 1. In the second case, it can be 1 or it can be 2. So far we've covered 1. We've given an example for 1, and we've given an example for 2024. If we can find an example for 2, we're done. We don't really need to find f, describe it specifically, although I think we can. But anyway, right now we just care about finding this. Can we find an example? Well, it's very easy. Just pick this example. F of x equals 1 whenever x is not 2024, and f of x is equal to 2 when x is equal to 2024. So this function actually works. You can easily see that because if you pick any set S cardinal and you do f of s, if it doesn't have 2024, then it's going to be just the set 1, which is cardinal. And if it has 2024 in it, then this set is going to be 2, and the other numbers, which is 1, and this thing is cardinal. So yeah, it works. So yeah, in total, that means that the answer is 1 to 2024, and in each one of them we can give an example. Here we can give example f of x equals 1, here the example that we just provided here, and here f of x equals x. They all work. And yeah, that means we're done. Again, this question was not really difficult. The approach was really direct. We started by simply experimenting. We immediately got f of 1 equals 1. Then for the 2, we got that we have two possibilities, 1 or 2. We saw that if we generalize this, if we look generally, of course here I put k in order for us to guarantee it's cardinal. Then if we just look at this, we have two possibilities. Our goal was to play with these guys to control f of k. So the only way to play with these is for f to be unbounded. If it's unbounded, we can play with this and immediately get f of k equals k. But if it's bounded, then we need to do a different approach. We just quote the infinite chain. Of course, we have infinite chain by the pigeonhole principle. You can just think about it, of course. And then we in this chain we immediately got that it must be all the values should be 1 and the others should be 2. Yeah, so it really wasn't that much difficult. Okay, so now let's move on to question 5. Problem 5 is a geometry question. We're given 3 points a1, a2, a3 on a circle gamma. They are given in counterclockwise order. Then we're given a random point P in the plane, and they are defining some geometric transformation here. So as you can see, this here is the counterclockwise rotation of the plane centered at AI. And what is the angle? The angle is actually the angle of rotation, basically. It's just the angle AI in the triangle. So basically each rotation I is the same as basically rotation with center AI with angle AI. Of course, it's counterclockwise. Okay, very good. They're defining the point PI to be the points of this composition, as you can see, of the 3 rotations. So we're going to rotate this point P 3 times actually in order to get PI. After we do that, of course, we're going to get 3 points, like P1, P2, P3, and we need we're going to take this triangle P1, P2, P3. Its circumradius. We need to show that it's less than or equal to the radius of gamma, the original radius of gamma. Okay, so if you want to do a quick sketch of this question, we have first of all the circle gamma, and we have the triangle here. Something like this. And then, okay, let's call this, name it A1, A2, A3. And we have a random point P here. What we'll be doing is simple. We're just going to, first of all, let's apply here. Let's find P1. To find P1, we're going to do the rotations like this. 1 plus 2 is 3. 1. And then 2 of P. Okay, so first of all, we're going to apply the rotation for 2. So we're just going to join A2P, and we're going to rotate this counterclockwise. What's the angle of rotation? It's the same as this. So we're going to rotate it maybe something like this. So this angle is equal to this angle. Okay, and we want to make it, of course, equal to it because we're rotating. So it's somewhere here. Let's call this maybe like P1 prime, maybe. And then we're going to do next step is we're going to take A1, going to join this, and we're going to rotate it again, of course, with this angle this time. So counterclockwise, so something like this. Okay. Yeah, I guess something like this. Finally, we're going to, of course, let's name this P1 prime prime. Finally, we're going to rotate this also counterclockwise with this angle. So something like this maybe. So eventually you're going to take P1 3 primes, and yeah, that's actually the point P1. This is the point P1. Okay, very good. Of course, we're going to do the same for the other ones, and eventually we'll get a triangle, and we need to show the circumcircle. The circumradius is less than the radius of gamma. Okay, how exactly can we deal with these rotations here? Of course, you can do this question synthetically. You can draw a very accurate diagram and notice something nice, actually. But here I choose to do this using some calculations, some bashing technique, because whenever I have actually rotations, one of my favorite techniques is to try complex bashing, because complex bashing is excellent way to represent rotations. So let's try to do that here. So of course we'll be taking the radius, the gamma to be the unit circle. So the radius here is 1, and our goal is to show the circumradius of P1, P2, P3 is less than or equal to 1. And of course our triangle here, A1, A2, A3, we're going to give them the numbers small a1, small a2, small a3, and let's set the angles here, this one and that one and that one, to be maybe alpha and beta and gamma. So basically these represent the a1, a2, a3, and the angles are represented by alpha, beta, gamma. Of course, don't forget that we know alpha times beta times gamma. What do I mean by these like represent the angles? I mean that these all going to be numbers that have like that lie on the unit circle, and they represent the angle. So the arc of this is the same as this thing here, and the arc of this represent this angle, and the arc of this represent this angle. And as we said, all of them have like they lie on the unit circle. Very good. So that means if you multiply these, actually the angle of this will be just 180. So actually their product is just -1, because three numbers, their argument is their arc is just 180 degrees, and all of them. But this number actually also lies on the unit circle. So yeah, that the only number that satisfies this is -1. Anyway, let's now try to work with this. Of course, we represent P by simple P. So let's first of all figure out P1 prime. So P1, here this represents P1 prime minus, we're doing a rotation here, look. We're rotating this there. So that means this thing here, this vector P1 prime minus A2, is going to be the rotation. What's the angle of rotation? It's just going to be beta, the angle beta, times P minus A2. Very good. So that automatically gives us P1 prime is beta P minus beta A2 plus A2. Found P1 prime. Okay, now let's do the same for P2 prime. Of course, we can do the same, but now we change to A1, and this thing becomes alpha, this thing becomes P minus A1. Again, we can do the same thing, but now we can plug the P, I mean here, of course, P1 prime. We can plug the P1 prime from here. So let's do that. It's going to be P2 prime. It's going to be alpha times this. So it's alpha beta P minus whatever, like alpha times that thing. Okay, here we expanded, we're multiplying by alpha. And then, sorry, I think here should be plus. Yeah, it should be plus. Plus, okay. Now we need to subtract alpha minus A1. Alpha times A1 plus A1. Very good. So this thing is just P2 prime. Okay, now we can do the same thing for 3. P3. Sorry, I think I'm messing up. Here we represented this with P1 prime prime. Yeah, P1 prime prime. And this thing should be 3 primes, which is eventually P1, right? So let's just represent this. Okay, we're going to do the same thing. This thing minus, but this time gamma is equal to, here A3, and here gamma, and here P1 prime prime minus A3. So that means P1 is going to be gamma times this. So I'm going to multiply this by gamma. So gamma, or let's say alpha, beta, gamma, P plus gamma times all of that thing. Minus gamma A3 plus A3. And that's actually P1. This is actually P1 itself. So we can say that this thing is actually P1. Very good. So indeed we found P1. P1 is let's write it again in an organized way. P1 is going to be, we're going to take the point P and we're going to multiply it by alpha, beta, gamma. Remember, this thing is just -1. So it's -P plus that thing here. If you look closely here, this thing actually doesn't depend on p. The only thing that depends on p is this thing here. So this thing is kind of a constant, a fixed, right? I think so. It's actually, let's call it maybe something like c1 maybe. So of course the same thing is going to happen for the others. Negative p for c2, and p3 is going to be negative p plus c3. Very good. So these are something like that. We found indeed the coordinates for p1, p2, p3. But now the main idea, the main question is how exactly can we represent the circumradius of p1, p2, p3? This triangle. Okay, we found the coordinates, but how can we find the circumradius? Because our goal, find the circumradius and then show it's less than 1. Well, guess what? There is one nice thing about these coordinates actually, which is that all of these are the same, right? Negative p, negative p, negative p. And guess what? When you have a triangle in the complex plane, it has some circumradius. If you shift it by adding or subtracting some number, it's still going to be the same radius, right? Circumradius. So guess what? We can literally do a transformation. We can multiply, subtract negative p. So we can literally cancel these and instead work with these guys here. So that means we can actually work with these new points, these edited points, c1, c2, c3. So given this triangle, c1, c2, c3, these are like the complex numbers that represent the triangle. We just need to show that the circumradius is less than 1. Now, what's the nice thing? The bad thing is we have no idea how to deal with this circumradius. But the good idea actually is, guess what? That means that we don't care about the original point P. As you saw, whatever the point P is, whatever it was, like let's say it was the orthocenter, maybe the incenter, the circumcenter, whatever it was originally, any random point, it's going to get deleted here. So really it doesn't like matter. So we can actually choose the point P from the beginning, whatever we want. So what we've done so far is we've just shown this claim. We can write like a claim. No matter what the point P is, the circumradius of this circle is going to be fixed. And this is the proof, because it's the circumradius of this triangle. So that simply means that we can now go to the geometry and choose point P wisely. So let's just do that. We can choose whatever point we want. Let's try to pick a point that's nice when we do rotations. Here we have triangle. Okay, what do you think is the best point, the easiest point to deal with for rotations? Think about it. Clearly it should be like a well known like center of a triangle, right? What do you suggest? One idea is to try O. If you try O, a circumradius, okay, that's good, because when you rotate it like this, you're going to get still the same length. But the problem is when you like continue, it's really not that much elegant. Okay, like these guys, this equal to this, but this thing really we don't know anything about it. So not that much of a great choice. You can choose maybe the centroid is really a very bad idea. We don't know anything about the angles nor the lengths. You might think about H, the orthocenter. Also, it's not very cool. Although we do know the angles, it's really not very cool. The only thing that, in my opinion, is very nice is to choose the incenter. If you choose the incenter, now you will see the magic. Notice that if you take A to I, this thing is then incenter, right? So this angle is equal to this. So that means when you rotate it, and you want to make this angle equal to this, you just need to make the angle equal to this, right? And guess what? Because this is equal to this, that means we're just doing a reflection. So instead of doing a rotation, we're just literally reflecting. So that means the original point, we're just reflecting it. Of course, let's choose a better I, because as you know, I has like it's the center of the contact triangle, right? It's like the center of the incircle. So yeah, we're going to have something like this. We're just reflecting this here. So let's say we have this point now. Very cool. What next? After we got this point, now we're going to do the same thing. We're going to take this, draw this, and Guess what now? Since this thing is a reflection, what's the point that is going to give us what we want? Like we're going to do something here so that this is equal to this. What do you think? Well, and of course we know that this angle here is equal to this. Well, let's try to do the calculations here. If you look at this thing so far, this thing is equal to this. And you can actually see that in fact, if you join this thing is a kite. It's a kite because we just like take this and reflect it here. So that means this angle is equal to this, and hence it's a over 2, a over 2. So this is a over 2. So when you rotate this with a, we're just literally going to get I again, which is super nice. So that means the first point, P1 prime, is this, but this thing is the P1 prime prime. Very cool. So guess what? We got I again. So now it should be very easy for us to get the rest. Now we're just going to take this thing here, and again we're just going to take this, so we're just literally reflecting it here. I. So guess what? This thing is indeed is our point P1. And hence, after all of that, we just got that if you just literally have a triangle and you took I, the first point P1 is going just to be the reflection here. The other point similarly going to be the reflections here, and the other reflection here. And this is our triangle P1, P2, P3. And hence, what does that mean? What is the circumradius of this triangle? Guess what? This triangle, you can now take a homotety centered at this point I, with like a scale factor half. It's just going to give you the original triangle, the contact triangle, which has circumradius small r, right? Small r. So that means the big triangle is 2r. So very good. That means we indeed found, guess what? We found the circumradius. It's fixed for all of those triangles for any point P. It's going to be 2r. 2r. And we guess what? Our goal is to show 2r is less than 1. That is r. And this thing is the case what? It's very famous, well known. It's called the Euler inequality. By the way, the proof for this, it's well known, so you don't really need to prove it. But anyway, we did prove this in our AGMO playlist, geometry. Listen to the theory part, I think the practice part, where we showed that OI square is something like that. I think it was r times r minus 2r. Anyway, this thing is clearly positive. So yeah, we do have this. It's very well known. So actually we're done. That's it. So again, as we saw, in order to deal with these rotations, we try to use complex numbers, and complex numbers are very simple, very easy to deal with rotations. The main idea was we don't really have a clue how to find the radius of this circumradius, but our main point was to show that these guys don't matter. They don't matter. Whatever you choose P, it's going to be the same circumradius. So that just means we can pick the P that we want. The best P was I, and I was very easy to deal with. So yeah, that's it, we're done. Of course, you can do a synthetic proof for this, but yeah, this is what actually I thought of personally. And I really do stress that complex numbers are very important to deal with rotations. So make sure you learn these. Alright, our last question is problem 6. As you can see, we're given two quantities, an and bn, such that an is the square root of n squared plus 1 plus root n squared plus 3 and so on till root n squared plus 2n minus 1. Same thing goes for bn, is root n squared plus 2, n squared plus 4, and so on till n squared plus 2n. We need to determine all positive integers such that the floor of an is equal to the floor of bn. As you know, the floor function is just the largest integer n such that x is greater than or equal to n. So for example, the floor of 3.4 is just 3. Yeah. Floor 0.5 is just 0. And just one thing you should know is we can write any number as its floor plus the fractional part of it. So this thing is the fractional part, which is just a quantity between 0 and 1. This thing is between 0 and 1. It should be strictly less than 1 and greater than or equal to 0. This is the fractional part. Okay, so with that in mind, let's try to start working with our quantities an and bn. So our goal is to try to work with this thing here, n squared plus 1, n squared plus 3, and so on, n squared plus 2n minus 1. Okay, let's try to look at the floor of this thing here. Okay, in order to deal with the floor, that is the integer part, we should look at each one of these and try to estimate what is the floor of each one of these, right? Let's try to do that. If you look at this thing here, what is it exactly? This thing here is an n square, right? N squared plus 1. So the root of this is approximately is going to be n. Same thing here, actually, it goes like to n. And so on. This thing is also, at least it should be strictly greater than n. But what about n plus 1? Is it like n plus 1 maybe? Well, actually, if you look at it, the stuff inside, for all of them, they're all greater than n squared. So yeah, all of them are, like the root of them, it should be greater than n. But they're all actually less than n plus 1 all squared. Because this thing is just n squared plus 2n plus 1. As you can see, the greatest one here, it's minus 1. So yeah, that means all of these guys are less than n plus 1 all squared. So when you take the square root, it's going to be less than n plus 1. So with that in mind, that means each single one of these is going to give us n point some stuff. N point some stuff, right? So one nice thing here, one nice idea is to get the n from each one of these outside. So each one of these is going to spit an n outside, and it's going to start to stay with some fractional part. So you can just say here something like this. This thing is equal to plus 1 minus n plus n squared plus 3 minus n, and so on, 2n minus 1 minus n. And as like, of course, each one of them is spitting an n. So how many n do we have here? 1, 3, and so on till 2n minus 1. Of course, we have exactly n number. So that means here we have an additional n square here, like n n's, which is just the n square. Of course, one thing to keep in mind, which is the floor function. When you have an integer, when you add an integer, then you can just take it outside. It doesn't really affect this thing. You can check it. It's always correct forever, like for whatever a real number x we have. Okay, so that means automatically we can delete the n square outside. So we can just say that this thing is n square plus that. So now we can just work with these. Minus n plus root n square plus 3 minus n, and so on. You might be wondering why exactly do we do this? Wasn't it before more beautiful? But actually no. Remember, we don't want to get fooled by these. We want exactly to know what exactly is the floor, right? So now each one of these is actually less than 1. But the problem is now we're having negatives. Is it really more elegant to deal with negatives and or the positives? Remember, like going from here to here is a kind of necessity, because we want to know exactly what's happening, right? So now, okay, each one of these is a fractional part. But yes, clearly, if you're working with positives, especially with inequalities, it's better than negatives. So what can we do now? Can we turn these into positive? Well, actually, this should be a familiar trick for you. This idea is very famous, which is especially when you're dealing with floors. You can easily change this into positive by multiplying by the conjugate, right? So if you multiply by the conjugate, you can easily write this as square plus. This thing becomes n squared plus 1 minus n squared. So it becomes 1 over root n squared plus 1 plus n. So we multiplied both numerator and denominator by the conjugate. You can do the same for the others. Now if you multiply the conjugate, you're going to get n squared plus 3 minus n squared. So you're going to get 3 divided by root n squared plus 3 plus n, so on, till we get here. We're going to have 2n minus 1 divided by root n squared plus 2n minus 1 plus n. Excellent. Okay, nice. So now as you can see, we turn this into like everything positive, so this is kind of nice. Very good. By the way, if you like remember when we're working with Bn, we're going to do exactly the same thing, and nothing will change. Still, these guys are smaller than 2n plus 1, and all of these exactly the same thing. We can do the same thing, and we're going to get exactly the same thing. So the other one actually is just going to be n squared plus the same thing for this, but everything like 1 swapped with 2, 3 swapped with 4, and so on. Here and here, of course. Okay, so that means these guys will cancel, so we shouldn't really pay attention to these. So we can now just think about this thing here. How exactly can we now find the floor of this thing? Okay, now looking at the numerators, they are nice, but the denominators are really ugly. How can we exactly deal with this stuff here? Remember, our goal is to play with inequalities, and clearly these numbers are kind of small, right? They're all fractions. So one idea is to try to do some inequalities here. And when we're working with inequalities of ugly stuff, it's totally okay to try using some dumb inequalities. By dumb inequalities, I mean some inequalities like maybe 1 is greater than 0.5 or something. Or maybe like 3 is greater than 1. Yeah, something like very bad. But we don't really care about that much accuracy here. So what exactly can we do? Because the denominators are really ugly, we can do one trick here, which is we can bound the denominators. How exactly? Well, we know that each fraction, each square root here, it's going to be greater than n and less than n plus 1. So we can simply do the following. If we call this thing here maybe let's call it c, then we know that c is first of all like one thing in general, root n square plus k, it's greater than n less than n plus 1. By the way, it's strictly. So now when you add n to it, add n to both sides, you get 2n here and 2n plus 1 here. So now if you take the reciprocal of this, you're going to get 1 over n squared plus k. This is going to flip. This is going to flip. So now we have this nice inequality. This one we can use it to our advantage here. So instead of each fraction, we're going just to multiply by these guys. So now we can just say that the floor of an, let's write it here, is bounded by, of course, n square here and then n square here. We can add the rest. So here we can add 1 over 2n plus 1 plus 3 over 2n plus 1 plus so on till 2n minus 1 over 2n plus 1. So now it became just 1 plus 3 plus 5 so on till 2n minus 1 divided by 2n plus 1. Same thing here, 2 plus 4 so on till 2n divided by 2n. Okay, now this thing is just, we can now calculate these. n square. What exactly is this? Of course, this thing is well known. You just have here sum of consecutive odd numbers. You can just do it. The sum of the first number plus the last number. 2n divided by 2, it's n, times the number of numbers, so it's just n squared divided by 2n plus 1. And this thing here is just going to be oh sorry, what am I doing? Here's the same. 1 plus 3, I mean, and so on. So it's also n squared divided by 2n. Okay, very nice. So that just means that this thing is between n squared plus, okay, here of course becomes n over 2. Here it becomes, okay, it's very close to n over 2. In fact, it's n over, if you divide by n, both numerator and denominator, it's n over 2 plus 1 over n, right? So they're kind of n over 2 and n over 2, if you think about it. Okay, our goal, of course, is to go for this, the floor of this. Can we know the floor of this? We provided a very good bounding, actually. As you can see, the bounding here is very close. Like this thing is nearly nothing. So it's nearly like this thing is very approximately this thing, n squared plus n over 2. But we really need to find the floor exactly. How can we find the floor exactly? Well, one thing here is that the idea is basically, if you like, let's take the number line, and let's take this thing here, this n squared plus n over 2. So this thing clearly is either an integer if n was even, or it's like an integer plus a half, right? Something 0.5. Okay, very good. However, now this thing here, of course, we know that the floor of an is before it, somewhere here. But this thing here, if you look at it, it's going to be very close to this. If we can show actually that this thing here, it's going to be less than, sorry, I mean like greater than this, or let's say like this number here, n squared plus n minus 1 over 2. So let's say this number is somewhere here. If we can show that this thing here, it's somewhere here, then that means the floor of an is going to be somewhere here, right? Between them. And this is of course going to give us the value for the floor of an, because basically this thing here, the floor of an, it's going to be, if we say it's between these guys here, if this was an integer, and if n was even, this thing is an integer, then that means the floor of an is going to be the floor of this, But if this thing was not an integer, let's say it was like n was odd, so it's going to be something 0.5. Since floor of an is here, then that means also the floor of an is going to be the floor of this thing, because then this thing is an integer, so the floor of it actually is going to be equal exactly to this. So again, that means if we can show that this here is greater than this, let's actually try to show it. We just need to show that n over 2 plus 1 over n is greater than n minus 1 divided by 2. This is equivalent to showing 2n is greater than 2n minus 2 plus n minus 1 over n. And of course that's just, we can just do it here. 1 minus 1 over n is equivalent to, we cancel this with this, negative 2 plus 1 is negative 1. So it's just 0 greater than negative 1 over n, which is correct. Okay, very good. So indeed it is true. So that means this thing here is greater than n squared plus n minus 1 divided by 2. So because the floor of an is strictly less than this and strictly greater than this, then that just means that the floor of an must be equal to the floor of this. So now we just concluded that the floor of an is going to be n squared plus the floor of n minus 1 divided by 2. This is what we've proven. Very nice. Of course, if n is even or odd, we can actually exactly know what is this. Very cool. Again, if you're not convinced with this, think about it like this. We know that an, or not an, let's say the that part here, without n squared, if we subtract n squared, not to worry about n squared, don't worry about it that much, it's an integer after all. This number is going to be between n over 2 and between this thing, n minus 1 over 2. So that means, because here the distance between these guys is too small, it's actually like kind of half. So the floor, since an is strictly less than over 2, n over 2, and n over 2 is either an integer. If it was an integer, then clearly an is not going to reach this, because remember the floor takes it down. So if this thing is an integer, then this thing is less than an integer, so it's going to be close to this. So they both are going to share the same floor. In fact, the floor exactly will be n minus 2, not 1 over 2. But anyway, we don't care. They both going to have the same floor. That's our point. And if it was not even, if it was odd, then this thing is not an integer, and hence this thing is going to be an integer. So an is going to be also, the floor of it is going to be exactly equal to this, and hence in both In both, of course, ways, we just get that the floor of an is just going to be equal to this. Of course, now we can do the same thing for floor of bn. Now let's try to do the same thing. Again, floor of bn is going to be between n square and n square. Here is going to be the sum of the even numbers. The sum of the even numbers, it's actually very similar. 2 plus 4 plus and so on till 2n. With the first number plus the last number, 2 plus 2n divided by 2. So it's n plus 1 times the number of numbers. So it's n times n plus 1. So let's write it here. So now it's n times n plus 1 divided by 2n plus 1 here. And here, sorry, plus n times n plus 1 divided by n square. Sorry, not n square, I mean just 2n. So again, it's going to cancel. So we can just actually write this. Here we're going to cancel it, so n plus 1 over 2. And here we can do the same thing we did before. We try to make it the same. N plus 1 over 2 plus 1 over n. So again, these are very close to each other. We can do the same thing. Our goal is to show this thing is true. Of course, here what are we going to do? Here we just want to do this, n over 2. We just want to distance to be less than half, right? Half. So of course you can prove this easily. Let's do it. This is the same as showing 2n plus 2 greater than 2n plus 1. Of course this is true. Very good. So we've just shown this, and again with the same reasoning we just get that floor of Bn is just going to be n squared plus the floor of n over 2. For the same reason exactly. Again, we have two cases. Either this thing is an integer or not. If it's an integer, then clearly Bn cannot, the floor of it cannot be this. It must be this thing minus 1. And actually it's exactly going to be the same as the floor of this. And if this thing was not an integer, so it's going to be something 0.5. So this thing is going to be an integer, and the floor is thus going to be the same as this. So indeed we found the floor of Bn and we found the floor of An. Remember, the floor of An was just n squared plus n minus 1 divided by 2. Yeah, that was it. So now when are these guys equal? If these guys are equal, then this thing is equivalent to saying the floor of n over 2 is equal to the floor of n minus 1 over 2. Clearly this thing is correct when n is odd or even. If n was even, then this thing is going to be, the floor of it is going to be n over 2 because it's an integer. This thing is going to be n minus 1 over 2 minus 1. So no, when n is even, they are not equal. But when n is odd, this thing, n over 2 is not an integer. So it's going to be just n minus 1 divided by 2. This thing is an integer, so it's actually n minus 1 over 2. And hence they are equal. So the answer is just n is odd. Any odd number will work. And that finished the proof. Again, a quick recap for this question. First of all, we started by working with this thing, the floor of it. Remember, when you're working with the floor, you need to know each part, what is its floor. So we just need to do approximations. Clearly, this thing is nearly n. So we just did that. We added n and subtracted n. Each one is going to give us an n. So here we're going to have n n's, so it's n squared. And each one of these is negative an n. Now after we did that, we got the n squared outside. And each single quantity of these is having a negative. And as you know, a very nice trick here is to just multiply by the conjugate, both numerators and denominators. Keep this idea in your mind. It's very important, especially when you're working with inequalities or algebra in general. Now we just made everything positive, and thus it's easier to do comparison. See here, it is actually a very common question, like compare between these stuff, something like that. Which one is bigger? This comes in regional math Olympiads. So you just multiply both by the conjugate, and now it's very easy. You just made them a sum. Okay, anyway, we just did that, and hence now we started working on this. How can we work with this? This is so ugly. These guys are nice, but the denominators are very ugly. So what we did was simple. We used a dumb inequality, which is to make these guys here, like get rid of them, make them very simple, which is simply root n squared plus k is greater than n, less than n plus 1. Once we did that, we were able to find this very nice thing. And hence, when we plugged it in, we just found this inequality here. And we saw that this thing is nice, just gave us n squared plus n over 2. But the nicer thing was this thing is really not that much beautiful. So what we did is we made it n minus 1 divided by 2. Now, that gave us the floor immediately. We knew exactly what is the floor. And we followed the same pattern for Bn, and we were done. Yeah, so that's it. Alright, so as a recap, this INMO was really not that much difficult compared to other years. Like you can say it's medium, between medium and like actually kind of most of the let's say first 3 problems I think were not really difficult, as you can see. Problem 1 was a really beautiful and nice geometry problem. It was suitable like as a problem 1. The idea was we just the phantom point, or basically the first idea was that you should draw really an accurate diagram in order to see that in fact O is going to lie on the side BC. Once you see that, really you can easily check that. If you can prove this, then you're done. So now our main goal is to prove this, and in order to prove this, we just choose a phantom point here, or prime, that satisfy these guys are equal, and it lies on the side. Then of course we just found this angle easily, and hence it's 360 minus 2 times this angle, and that just finished the proof, because this thing is indeed the circumcenter of the triangle, and thus we're done. For the problem 2, it was really an easy question. We immediately started by picking the most reasonable, like logical. It was really a greedy algorithm here. We immediately just picked like each row 1000, 1000, 1000, and then we just like pick these columns, the 1000 for each one of them, and it was indeed the best strategy. We could easily prove that by just like taking a random row and just like what we did. Very simple inequality. For question 3, that was a nice standard like a number theory question. We just took a prime number here, and for each one of these we turned this into mod, and in order not to work with 2 numbers, we just did the division strategy, and thus we're now working with the numbers x, y, and z. Their product is 1, of course, don't forget that, and we know that like x to the 20, 23, and so on, they are just -1. Now we're working with this question instead, and we can easily play with this, mix this with these in order to get x is -z. So we found z. Now since we found z, we can find a relation from here between x and y, and furthermore we can do a relation between this and this and find that x squared is -1, and hence easily we found that y actually is 1, which gave us a contradiction that b should be 2, which is not, since it's odd. For question 4, that was like where the questions got a little harder, but still it's really like a logical question. First of all, you just start by taking a cardinal set, exploring the question, very simple cardinal set with just one element, 1. So we got f of 1 equals 1. When we move to 2, we saw it has 2 values, either 1 or 2. So we try just to generalize what we're doing here by taking k and some numbers. We saw that in order to control these, we need f to be unbounded. If it's unbounded, it was easy to get to get rid of this case by getting immediately fk equals k. But if it was bounded actually, then we need to discuss it in a different manner. We simply took an infinite chain, and then we just easily actually just picked the numbers in this chain. We got that this chain, all of the values should be 1. All of the images should be 1, and hence immediately it gave us the f24 is 1. So we move to the other case. The other case basically here. I mean actually we have 2 cases. Either f is 1 for all of them or not. So if f is 1 for all of them, then we're done. If not, then assume we have something that's not 1. We can just pick our original chain, infinite chain, and we can pick this new number, which immediately gave us this number should be 2. Remember, we didn't really describe the function, how many numbers are have f there, f is 2, but who cares? We just want to have the f of 2024. Okay, so that was question 4. For question 5, Question 5 was really kind of a weird question because, oh, we have 3 rotations and you might feel like stuck. How can we deal with 3 rotations? As we said, there is a synthetic proof for this. You can look at this at the AOPS. But here, what we did was follow a complex number approach, complex bashing approach, because really rotations are very simply handled with these. So we just did a complex bashing. Immediately, it gave us that we have this nice thing. And as you know, when you have something like this, then you can shift by negative p, and hence you just get these numbers. So we just got that actually it doesn't matter. Whatever point you're going to pick, the circumradius is invariant. So why not picking the easiest one? Let's pick I. Once we pick I, it's a piece of cake. We just get 2 small r, 2 times the radius, which is less than r by the Euler's inequality. Okay, so finally the last question, problem 6. That was quite a nice question, probably the nicest one in the exam, because in this one we needed to use kind of many ideas to deal with the floor. First of all, these ideas are also standard to dealing with floors. You just need to catch every single thing, see what exactly is the floor of it. We saw that it should be n for all of them. And then we just follow this standard idea, actually classical idea, multiplying by the conjugate, and then we used some dumb inequalities to make everything easy for us. Once we did that, we just did some simple bounding, and we got the floor exactly for each single value for an and bn, and hence for them to be equal, n should be odd, as we saw. Yeah, so that was the paper for INMO. Let me know what you guys think about this paper. I hope you enjoyed the video, and please don't forget to like, share, and subscribe to the channel, and of course join the Discord server where you can of course discuss these problems furthermore with the other students preparing for Math Olympiad contest as well, and you can also check the resources we're sending there, many cool stuff. So see you guys in the next video.